So I'm going to talk about using GPUs with Python. And there are several questions you may have, which is what is GPU acceleration? How do I enable GPUs, for instance, to use CUDA in Python code? And how do I deploy GPUs at HPC2N, UPPMAX, LUNARC, NSC, PDC, and C3SE? So this is an intro to common schemes for GPU code acceleration, or at least a little bit, mostly number. Uh, we will learn a little bit about the GPU nodes at HPC2N, UPMAX, LUNARC, NSC, PDC, and C3SE. I will focus on NSC and C3SE because those are the NAISS systems, and PDC is also a NAISS system, but it doesn't have NVIDIA GPUs, it has AMD GPUs. And I will talk more about that in a moment. And I will show you how to make a batch script that allocates GPU nodes for these centers. So to understand the capabilities of a GPU, you should compare it to a pure CPU. And there is a schematic here of a CPU architecture. And this shows a typical CPU single node. There are here 256 cores. Each has cache memory, L1, L2, and L3 cache. And you can see that the L3 cache is shared within several nodes. And the CPU node is divided into two NUMA nodes, where they have a shared socket and shared memory. You can address the memory on the other socket, but it is ever so slightly slower to address memory on this socket if you're sitting here and opposite, but not enough that it's really something to think about. But there is some difference. And then there is local disk that is connected to this node. And most of the systems, with the exception of Dardel, I believe. And then, of course, there is network connected to it, which could be Ethernet and various types of open fabric, InfiniBand and things like this, and other I/O. And in this case, they have 378 gigabyte per NUMA node on these ones. This is an AMD Zen 4 node, which has a base frequency of 2.25 gigahertz, but it's possible to boost this frequency up to 3.1 gigahertz. And that is something that would require a reboot of the node to do so. As for GPU architecture, here is an example of a GPU card of the type Ada Lovelace, and that is the types that are in the L40Ss. Which are, for instance, at HPC2N, and also Pelle got the L40Ss. And when you compare them, you can see immediately that a main difference is that there is a lot more cores, but it is smaller cores. So they can't do a lot each of them, but there is many of them. So if something is very parallelizable, then it will run faster on this one. And they all share the L2 cache. This also has some FP64 cores that are not depicted in the diagram, but this shows the CUDA cores, the tensor cores, and in this case also the RT codes, the raster graphics ones. And this type of GPU has three types of cores. So the one that you would usually think about, the CUDA core, is the one that is good for regular GPU programming, high performance computing, things like matrix multiplications and things like this. Whereas the tensor cores has lower precision, and they are usually the ones you think about when you want to use them for machine learning, for instance. And these cores are arranged in the slots called SMs, or streaming multiprocessors. And you should just think of it as a bunch of cores that are sitting together. And this is a zoom in on one of those. And you can see there are both the CUDA core and these are the tensor cores, and then the RT cores. So not all GPUs will have all these types. The original ones had only CUDA cores, and most now have also tensor cores. If you're comparing this, which is an NVIDIA GPU, to the AMD GPUs, then what is similar to tensor cores is at AMD called matrix cores. But they are doing basically the same thing. If you have a typical cluster, then you would have GPUs that are attached to a CPU, and that means you have a CPU-GPU hybrid architecture. And in this case, you would call the CPU component the host, and the GPU would be the device. And in this case, also, when you are allocating the GPU, no one else can use the CPU, which means that that too will be something that goes into the cost when you allocate it, because it's simply both of it both of it will be allocated because you can't use the CPU on a node that someone is using the GPU on. So if you can program it that way, then you could use both the CPU and the GPU, which is also a good idea, but it takes more to implement, of course. This is an example of how it would look when you have a GPU node, in this case on Kebnekaise. It has two L40Ss that are sitting on a regular AMD Zen 4 node. And you can see this is the Zen 4 node. And each of the sockets in this is connected to a GPU card. So you could allocate just one half of the node, one socket of the node, and you do that when you get one GPU card. So it's possible to use this one while someone else is using that one, of course. So this is a hybrid CPU-GPU architecture. And the Numa Island has 24 cores, regular CPU cores, for a total of 48 cores. And the GPU card are connected with a PCIe interconnect. So that means data transfer is actually pretty slow. So characterizing CPU and GPU performance, when you compare them, you will think of latency and you will think of throughput. Latency, that is the time you spend in one computation. Throughput is the number of computations that you can perform in parallel. And that means you will say that a CPU has a low latency because it can do very fast computations, but it has low throughput because you can only do a few computations simultaneously. On the other hand, GPUs has high latency and high throughput. So you can do lots of computation, but not very fast. So needs to be very parallelized. And you can look at it like cars on roads. A CPU would be a more compact road. There's only a few racing cars that drive there, but they go fast. A GPU, on the other hand, would be a road that looked like this. There is space for many more cars. It's broader, but they don't drive very fast. So that is a good way of thinking of it if you want to remember it easily. So not every Python program is suitable for GPU acceleration. GPUs process simple functions rapidly, as I said, and you need repetitive, highly parallel computing tasks to use them to their fullest effect. Originally, you made GPUs to render high-resolution images and video concurrently and fast, but they can also perform any other parallel operations on multiple sets of data. So now they are very often also used for non-graphical tasks. And some very common uses are machine learning and scientific computations, where the GPUs can take advantage of massive parallelism. And when you are looking at a GPU, you would say that if it's good for machine learning, then it usually has many tensor cores. Whereas if it's more generalized GPU computation, high performance computing, you would want something with a lot of CUDA cores. It is not uh, always so, but generally you can say this is the case. Many Python packages are not CUDA aware or cannot be used on GPUs. Some have been written specifically with GPUs in mind. So if you usually work with something like NumPy and SciPy, you would optimize your code for GPUs by using CuPy instead, that mimics NumPy, or Numba, which has bindings to CUDA, and that means you can write CUDA kernels in Python yourself. Numba is very much used in general computation on GPUs. You can use custom algorithms, that's for NVIDIA GPUs. You cannot easily use it on AMD GPUs. Number previously had support actually for AMD GPUs, but no longer. So now you would use HIP. And yeah, as I said, mostly or in many cases, it's used for machine learning or deep learning. And there you would use TensorFlow or PyTorch. And these can handle both CPUs and GPU processing internally without the programmer having to do anything specifically. And that is something that will be covered by Jayant later today. So let us move on to the GPUs that are at these HPC systems here in Sweden. Either there are no GPUs on the login node, or if there are, you can't access them for computations. That means you need to use either an interactive job or a batch job in order to access them. Now, the interactive job could either be a regular interactive job started with interactive or salloc or something like this, or maybe more likely through a graphical interface, for instance, in Jupyter or through one of these desktop on-demand systems. But regardless, let us here look at it if you're doing it as a batch job, because then you would submit a batch job, and inside that, or in the interactive command, you would have to add some specific lines. And those lines are one of the things that is most different between the system, because partially because they have different GPUs at different systems, but also simply because some are using a partition to allocate them and some are just using another command. So if you are, for instance, at UPPMAX on Pelle, Pelle now has L40Ss and H100s. In either case, you say, I want to use a GPU partition, and then you use this command here to say which type of GPUs and how many cards. How many cards? You see that here. If it's H100s, at most 2. If it's L40Ss, at most 10. HPC2N has a ton of different GPUs, and there you use 2 lines one that says how many GPU cards you want, which is one of these here. And the other one is minus capital C and the type. And type is one of those GPUs here. If you only give this one line here, you would get a random GPU, and it probably isn't a good thing because, for instance, you could end up on an AMD GPU, which you don't want if you have a CUDA code. So say how many cards and what type, and you can see how many cards from the type. So if it was an L40S, you could go up to 2 or up to 6, depending on node. LUNARC also uses partitions like they do on UPPMAX's Pelle, and you just say how many GPUs after you're saying which partition type. NSC Tetralit has NVIDIA T4 GPUs, fairly old GPUs. There's one on each node. And you would need to add these 3 lines here in order to get a GPU. PDC has AMD GPUs, and here you will say you need the GPU partition. Everything on PDC is partitions when you're asking for different parts of the system. So you also use that when you are doing regular CPU computations. You're asking for main or shared or large, depending on what type of how many nodes you need and if you need them exclusively and things like this. Here we want the GPU partition. And then we also have these 2 lines here, the full node, and then how many tasks per node, because we're only running on this GPU. Then C3SE, Alvis, is meant only for GPU jobs. No node sharing, so exclusive is automatic. You always get the node on your own. It doesn't mean you get one full node, but you do get no one else is going to use it at the same time. That's what I wanted to say. And here you use these 3 lines, and that means that you just say one node if you just want one GPU, 2 if you want several or more. Type can be one of these, and card is how many there are on each type. Okay, so let's look at how that would seem in a actual batch script. And the example I'm going to use is number, because that is very much used. Number is installed on some of the centers as a module. There is a number installed on UPPMAX, but it had some issues with the driver. So if you're using that, you need to instead use the virtual environment that has been created for you. And that means that here at UPPMAX, you are simply sourcing. Why is this not showing the new one? There. You are sourcing this environment here in order to run it, either interactively or in batch. So this is an already created virtual environment that you can use, and that contains a number. But you can see here you are asking for the GPU partition, and here in this case one L40S. And you can also compare how long it takes. So you can see these were both L40Ss, and they were pretty fast on either one of them. So this is how HPC2N asks for an L40S. And LUNARC for an A100. And C3SE is here for T4, 2 of them. And NSC doesn't have number or at least it has a number, but it's not, it's again one that has a driver issue. So because of that, there is again a need to create a virtual environment. I have created one and it's located here, so you can just activate that. Otherwise, these are the steps for you to create it yourself. And that's if you need it at a later point. I don't have an example here for Dardel simply because there are no way to run number on it. There are some examples in the exercises day 4 directory. Also for PDC, there is a HIP example there. But if you are on Tetralit, so I'm going to go to, I fetched a new version of the tarball today, by the way. You should do the same because there were some minor changes. For instance, for these two systems here, for Tetralit or for UPPMAX. So if you're running on either of those two, get a new tarball. Inside the NSC directory under the exercises day 4, there are a number of GPU examples, and I'm going to look at the one that's called add list, which is the one we are running here. So I'm opening it, and here I'm going to use this already created virtual environment, and I also load these modules here. It is not needed at Tetralit, but I'm doing it anyway. Didn't seem to be a difference between running it with or without. So I think it's easier to simply put them there always, instead of trying to remember that it's different at Tetralit. Of course, if you're just using Tetralit, it's not a problem. But since I was testing on 6 different systems, I would have just confused myself by trying to remember where to put it or not. I need to make a change to this one line, and that is to put my name here. This is a path to where I have my exercises. And it should just run for 5 minutes. So now I will save it. Like that. And I will submit it. It probably will take a while to get it to run because there seems to be quite a lot of use on the GPU nodes right now. Meanwhile, I will just quickly show you where this, I need to go out one more and one more here. Here is the number GPU environment that was created. So it is, if you are on Tetralit, in project courses fall and then number GPU. So you would, as shown inside of this example here, just source it. And the path for it on Pelle is shown here. The others all have a number that works. This one here at Alvis loads everything. So I can try and show what happens here. You see I have nothing loaded. If I'm loading number CUDA, then that should load enormous amounts of other modules. So you can see here, so that loads everything. Python and SciPy bundles and Python bundles and number. So it's easy to just use that one there if you need number. Let's see if this has finished running. No. I'm going to go ahead and submit it on Elvis as well. It was 6 weeks, yes. I need to make the change to add my name here. And on Alvis, I called my directory like this. So this is the one thing you need to change. Put in the name you put yourself here. The reason I'm creating this environment variable called myPath is because I have a directory for each of the centers, and then there's also directory programs where the programs themselves are located. So actually this should say myPath. That is an error. So if you're on Alvis, you need to add that. Otherwise, it will not be able to find the Python script. Yes. So you see, if you go up here, there is one directory for each of the centers, and there's a directory programs. And programs holds all these many different examples that we have used today, or that also some of those that Pedro was working with, as you can see here. I need to submit this. And it's not running yet. Let's see. It will run eventually. And this ran now. And I need to go back to my directory. And you can see there is now a file here, slurm minus jobid.out, which is the default name that you get when you are running a batch script. And you can just look inside it with cat. And it seems that I also forgot to add this path in this one. Sorry. No, it's there. It's weird. Okay, I will look at this later and figure out why it couldn't find. Let's try and do this. ls. Ah, I probably forgot the user. Yes. If you're at NSC, you also need to add users here. Sorry, I deleted too much when I updated it. So change the name to your name and then add users, and then it should be able to find it. I will continue while this is running because it will take some time to run. I have here these exercises. It's a continuation of the one that Pedro talked about, the integration 2D. And there is simply, this is simply meant to be an exercise where you try and do the same thing as what happens up here with the add list. So take maybe that example from the cluster that you are using, and then try and change that batch script in such a way that it can run these two. And in order to do that, of course, you can put both of those in the batch script. And the solutions are here also, but try if you can get it to run yourself first. So the answers are here. The answers are also in the exercise directory, but try it yourself first. And before you do that, also simply try and get the addlist.sh to run at the system you're at. It is located within the path, well, wherever you have downloaded it. You did a wget to get the tarball. And I put it in the project storage and then my subdirectory. And then this part here will come from the tarball. And I think that is all I wanted to say. No, I think I just want to very quickly open a one of the desktop on demands and show you how you could actually get the GPUs there, because you're probably going to use that in a little while. So let's try and use HPC2N as an example. The Alvis one will work very much the same, and the links to them are under interactive from yesterday. No, from Friday. Interactive there. There are links to all of them. But this is also what both I and Rebecca showed on Friday. But here you can either take the Kebnekaise desktop if you want to get a terminal to work in. And here the same things here as before. You in this case, you can pick between two different desktop environments that will vary depending on system. Pick the compute project you're in. And number of hours. 1 is the least, 12 is the most here. And I would suggest just 1 hour because it will take time to get otherwise, especially because now we are going to pick any GPU. And that means you will just get one GPU. And then let's launch it and see how long it takes to start. Meanwhile, I can try and also start a Jupyter notebook. And that is done exactly the same way, also like this here, except that there is no desktop environment to pick, and you can only pick either one core or any GPU. Again, there are these environments you can use if you want to install your own kernel. That is described on HPC2N's documentation pages. You can put your working directory. In this case, I'm putting the one for the project storage. You can otherwise select path. I'm launching that as well. Meanwhile, this desktop has started, so I will go there. And I'm opening a terminal that would otherwise be in here. System tools, terminal. I can see that I am on BCN 1715. I could do control show node BCN 1715 to see what type of a GPU I have here. And I can see I have an L40S. And I could run NVIDIA SMI, and that seems not to be there. It is, but I'm spelling it wrong. So you can use this here to see how many GPUs you have and that you actually have one here. And you do have one. So let's see. Meanwhile, maybe Jupyter has started, and it has. And when you just started first time, it will look like this. I would usually start a terminal first and simply use that to check what it is I got. Let's control show node to know that I'm actually running on a GPU. And I can see here that I have an H100 in this case. So yes, I'm actually running on a GPU. Okay. I'm going to delete those two because I'm not going to use them, so there's no reason to use the allocation for this. It will only make it slower to start for those others who are going to use this. And what I meant when I said that the description of how to do this was in the interactive on day 2. So you could go here to Desktop on Demand, and there will be a description of the different types of desktop on demand systems. And to recap, those are on Alvis and HPC2N that has a portal, and the GFX launcher is on Cosmos and on Dardel. If you're on either of the others, you have to use the command line as a regular SSH, though on Pele, you can also start the thin link and go in there and start a terminal, of course. Okay, let's stop here. And there's about 10 minutes until noon. I suggest try and use those time to get the add list to run, and then you can see if you can also modify the addlist.sh script in order to get the integration 2D and to run also. And after that, we have a lunch break until 1 o'clock. I am going to stop my share.